Hello students, in this video we have additional exercise problem 4.18. Three situations we are given, so we'll take up one by one. First one is a magnetic field that carries in magnitude, I suppose it should be varies. A magnetic field that varies, not carries. So a magnetic field that varies in magnitude and from point to point but has a constant direction east to west is set up in a chamber. A charged particle enters the chamber and travels undeflected along straight path with constant speed. What can you say about the initial velocity of the particle? Now let us try to understand the situation. The magnetic field is from east to west, so we can think of a situation where we have, say, a box, and let us put say north pole here and south pole here. So in this case, I can say that the magnetic field is from north to south. Now this is uniform magnetic field. You can have different situations like you can have this sort of situation and then the field will be non-uniform. You can have this sort of situation and then you will see your non-uniform magnetic field in this region. But sorry, should be south here. But in all the three cases, magnetic field is from our right to left, or else you may say it is from east to west. And for this situation, what we are told? We are told that in this situation, a charged particle enters the chamber and travels undeflected along the straight path. What we can say about initial velocity of particle? Now, if you see that the particle is entering into magnetic field, there has to be a force F is equal to QV cross B, isn't it? This force must be acting. And if I see that there is force acting, now magnetic force cannot change speed. That we must have studied in you must have studied in theory topics. So if speed is not changing, this force must change direction. And if direction is not changed, the conclusion should be that magnetic force is zero. Why magnetic force is zero? Particle is moving, magnetic field is also present. But then there is one more factor. F is equal to QVB sine theta. If sine theta is zero, force will be zero. And when sine theta will be zero? So if the particle is entering like this, where V and B both are parallel, in that case, it is possible that sine theta factor will be 0 and then force will be 0. So one possible reason why the particle goes undeflected or on straight path is that V and B must be parallel or anti-parallel. Then the force, magnetic force will be 0 and particle will go undeflected. So that is about situation A. Let us go to second situation B. What is the second situation? A charged particle enters an environment of strong and non-uniform magnetic field varying from point to point both in magnitude and direction and comes out of it following complicated trajectory. Complicated means it is neither straight line nor a circle or parabolic path. So there is no specific shape of path, so it is complicated path, complicated trajectory. Would its final speed be equal to that of initial speed if it suffered no collision with the environment? Yes. As mentioned earlier, magnetic force has nothing to do with speed. Magnetic force only changes direction of the particle and then speed will remain constant. So even if path is straight line or not straight line, any complicated path, but as long as it is only magnetic force, we can be sure about one thing: speed will remain constant, speed will not change. So answer is initial and final speed will remain same, provided there are no collisions or there are no other forces acting. Let us move to third one. See, an electron traveling west to east enters a chamber having a uniform electrostatic field in north to south direction. So now you have electric field prevailing north to south. Specify the direction in which uniform magnetic field should be set to prevent electron from deflecting from its straight path. We'll need to understand situation first. Say electron is going from west to east and electric field is from north to south. So let us first try to create that situation. So I have a particle, say electron, trying to go from west to east, so in this direction, and then I have electric field set up here. So I'll put positive charge on upper surface of this chamber and negative charge on lower surface of the chamber. So what will happen then? I can say that I have set up electric field which is from north to south, isn't it? See, electric field lines go from positive charge to negative charge. So what is the direction of electrostatic field in this region, in this chamber? It is from north to south. And in this field, our particle, our electron is entering. So what will happen? If you don't have any other force acting, this will not go straight. It will gradually be deflected in upward direction because positive charge is upward. So electron will experience force F is equal to QE. Okay, electron being negative charge. So if electric field is downward, the negative sign will push it upward, and hence the path of electron will be like this. Okay. Now we don't want the particle to go up. So what we'll have to do? We'll have to exert a force which can push this electron down and help it maintaining straight path. So who can be that force? That force has to be magnetic force. So F is equal to QVB. We'll have to apply. Let it be FB, not Facebook, but magnetic field, and F is equal to QE. Let it be FB. So if these two forces are equal and opposite, resultant force will be zero, and in that case we can say that the electron will go undeflected. So what we'll have to do? So we know that electron is going in upward direction, so I can say that Fe is EE in j cap direction, isn't it? Upward, let us consider upward direction to be positive y. So j cap, we'll have to establish magnetic field which is equal in magnitude but in downward direction, so minus j cap, and how much it will be? It will be QEB, sorry, QVB, so EVB. Okay, so now I know that FB has to be FB j cap, and we know that electron is going from west to east, so I can say that velocity vector is, can I say it is plus V I cap? Okay, so in this formula, Q V cross B, Q is charge of electron, so it is E. Instead of V, I will take V I cap and then B. So if we want the resultant force to be in positive y direction, what should I consider here? So apply your mind and find out that which option is possible. Should I take B to be in X direction? Should I take B to be in Y direction or Z direction, or negative X direction, negative Y direction, or negative Z direction? So values, one of the six values will give you answer J cap. Should it be I cross I, or I cross J, or I cross K, or the other three options? So find out, and that will tell you in which direction magnetic field should be applied. Okay, so try out and find out the resultant direction of magnetic field. Thank you.